Welcome to breadboarding. In the previous video we did the KeyCAD diagram for our 386 breadboard PC, and we went through in detail looking at the data buffers and latches, the address buffers and latches, and down the bottom we had all of the control logic and the clock for the CPU. So this is a picture of some of the components we're going to be using for making this. These are most of the new ones. There are a few that I had in stock already. I'll just take you through a few of these. So on the right hand side here you can see there's a lot of these chips here. These are 512K static RAM chips. Now the original DeskPro 386 that we're basing this on could actually have up to 10 megabytes of memory. So I've actually got 20 chips here. They're going to be quite fun to try and fit these into the breadboards, but to start with we're just going to be fitting 4 times 512K to give ourselves 2 megabytes of RAM to start with. Then some of the more difficult to come by chips. So these chips here are the memory mapper. This is the 74LS612. I have to get these off eBay. Some of the VIA keyboard PS2 mouse controller, the floppy disk controller, and the DMA controllers. Now what I should say is you can see that obviously most of these components are still available from suppliers like Mouser. The PLDs down here just come from the stock that I already had. So we're going to be wiring up the components on this side during this video. So this is video 11 in the 386 breadboard PC series, and in this video we're going to be wiring up the data and address bus, latches and buffers. So this is the board as we left it previously, and this is our breadboard adapter that we created for our 132-pin 386 processor. And we were testing it with these dip switches to write a very simple 4-byte test program to test out that the processor was working. And down here we've also got the reset power on supervisor circuit, the oscillator, and some of the reset and dividers we needed to drive the clock signals for the processor. So take a look at the board as it stands now. You can see what I've done is I've put in a lot of the power rails, tied the breadboards together with various connectors here. And in fact, I've disconnected, this is the test board, which has got the dip switches to set the data lines, testing the processor, so we don't need that for the moment. And this is the circuit that we developed in earlier videos with the reset clock and the buffers and the dividers necessary for the CPU clock. Now, in fact, with the diagram, we're going to need to fit this here. So I'm going to remove these components and put them up towards the top here, because we're going to need to feed the clock signal here into the high-speed clock for the CPU there. Now, as I've done for a lot of my other videos, I'm going to make use of chip labels. So these chip labels are produced in Inkscape, which is a scalable vector graphics program. And you can see here I've got the chip layout custom to each individual chip. So you can see here the U9, U19, this is the schematic reference. And I've actually put the correct pin labels on each of these chips. I just figured that when wiring things up with such a complex project, it probably will result in fewer problems, assuming that I've got the address labels right. You can then see we've got the address buffers and latches. And then along the right hand side here, these are all the programmable logic devices we're going to be needing to use for this part of the project. And you can see here the references that the original DeskPro documentation had. And we covered this over the last number of videos where I was converting the designs for these in the PDF design document, and we converted those into WinCUPL2 PLD files to program and test these chips. Then there's a couple of other gates and flip-flops down the bottom here. So I'm just going to go and cut those chip labels out, put them on the various chips, and we'll start laying out the chips. So the latches, the buffers, more latches down here, and I'll also I'll transfer all of the clock signal and put them on here. So I'm not going to video transferring these on here, because I've basically just got to transfer the stuff over onto here. Now there is a power connector up here, so this goes to the top of the board up the top right hand side here. You can't quite see it there, but this is the power distribution block that I've got, and this ensures that we've got low resistance paths to the power supply. In fact, I measured the resistance from the top here down to the corners here, and the resistance from here to here is only about 0.1 of an ohm, so there's a pretty good path down here. It should mean that even if we have a couple of amps going through this board, we should only drop a 0.2, 0.3 volts at worst. So as long as we're driving things at around 5 to 5.5 volts, we should certainly have good voltage down the bottom here. So I'll go off and stick all the chip labels on all the chips we're going to use and lay them out here, and when we come back, we'll start to wire everything up. Okay, so I've stuck all the chip labels on and I've laid out all the chips. So you can see here, these are the anti-static containers one. So there's the 74LS245, the ALS573 and the ALS541. So these are 573s, 245s, combination of 573 and a 245, 541s, and then another 541, and this is the 257 multiplexer for the A20 address handling. You can see here I've taken the test circuit that I had from the earlier videos and I've put that back down here, now matches the schematic. So now what I'm going to do is plugged all these in. There are a few extra ground lines I've needed to put in. So sometimes where the ground pin on the CPU here may have had two links going to ground there, and this is where some of these pins I was able to put a ground pin from underneath here into the bus rail here, but there's a couple of them I couldn't. So these two here and this one here are basically where we had the ground rail from the CPU connecting through here. So we just need to make sure those are on there. So all these now been plugged in and we've got the power connected up to them. What I'm going to do now is to hook up all the various signals. Now the key thing here is that because I arranged this breadboard adapter such that all of the data lines basically go straight into here. So these pins here go straight into here, and hopefully we're just going to have to wire up the SD lines. So SD0 to SD15 is going to need to go between these chips here. Then we need to put in the various control lines. So I'll just have a look at the schematic and see what we need to do. So here's a CPU. So we're going to be going in and wiring in the 245s, and you'll see here that we actually need to hook up the SD0 to SD7 lines, SD8 to SD15, and then in fact these repeat again, so SD0, SD8, SD15, and this is going from PD0 down the bottom all the way up to PD31, so our 32-bit address bus. So we'll come back to this diagram when we come to have a look at doing the control signals. So I'll just reposition the camera so you can see this bit a little bit more clearly. I'm just going to wire up all the SD0 to SD15, SD0 to SD15 up to these chips over here. Okay, so that's all of the SD lines plugged in between these two lots of chips now. At some point we do need to connect the PD0 to PD7 over to here, so we can use these sort of DuPont connectors and ribbon cables, so they will just fit in here. Now the only issue is you can only really fit one cable in comfortably. There is another row of holes there, but I think it's going to be a bit tight. So I think what we'll do is we'll use cables like this. However, when we put this in, we can't really see the board too clearly, so I'll leave that to a bit later on. So now what we need to do is to have a look at the control lines. So we've got the direction control. So there's a common direction control between all these chips, and you can see that it's sort of pin 1. Pin 1 down all here. Now the only issue here is if I wire all these up actually on the right hand side of the chip, then as we saw before, there's not very much space for putting in the DuPont connectors in there. So what I'm going to do is to route this over onto the other side down to here. And then we've also got another set of signals. Now these are the byte enable signals. So you see we've got byte enable 3 there, 2, 1, and in fact 0. So what I'm going to do is to collect all these signals together in a little block from 0 to 3 down the bottom here. And this should make it easier to wire up, because if we look at where this is going, we're going to need to wire these signals all the way up to here. So it's probably going to be easier to collect the signals together here, and then we can use some sort of ribbon cable to go all the way over here rather than having lots of wires sort of trailing across the board here. So I'm just going to go and wire those two control signals up. Okay, so we've got our byte enable 0 to 3 here, and here is the common direction control. So that's the control signals for these chips. So now if we look at these ones, you can see here the output enable, the LOE, so that has a common set of connections, and then for the byte clock we've got BK0, 1, 2 and 3. So I'm going to collect all these signals down the bottom here, a bit like we've just done with the byte enable signals there. Okay, so that's all of the data buffers and latches wired up. So we do need to wire in the pins from here over to here at some point, but I'll wait until the end to put all of those DuPont rainbow cables in. So now I'm going to need to wire in all of the address buffers. So I'll just move the camera over and then we'll come back and do that. So move the camera over. So we're going to be wiring up these chips here. I'm going to leave these pull-up resistors here for the moment. We will be sorting out these a little bit later in the series, but for the moment we'll just leave them. So let's just have a look at the KiCad schematic. So here we have the address side of the board. And you'll see that the PA2 to PA31 are all connected straight into these latches and this buffer chip already. But you'll notice that we don't have a PA0 and a PA1, and that's because we have these byte enable 0 to 3 here, which says which of the 32-bit data bytes is actually selected. So that effectively replaces the PA0 and the PA1. And you'll also see at the top here, we go up to PA23 and then we jump straight to 31. And in fact, the 24 to 30 are actually up on the top here, and we don't need to use those. The COMPAQ DeskPro 386 only decoded 16 megabytes of memory, which back in 1986 was an awful lot. And the PA31 address line is actually used to determine on the 32-bit memory board whether or not we're writing to the memory register, which controls certain things to do with the ROM shadowing. So if I have a look at the highlighting the buses, so we've got the processor address bus, and you'll see that the processor address bus comes out of here, and we don't really need to do anything for plugging into here. But you'll notice that these buffers over here, these are actually to take the ISA bus system address and feed that back into the processor address under direct memory access. So when bus hold acknowledge goes low, so this means that bus hold acknowledge when it goes high normally means that the processor has given up the buses for use with DMA or other bus masters. So in fact, when this goes low, then in fact this enables this to take the data from the ISA bus and pass it through to the processor side. And the reason for that is the 32-bit memory board, which I'm starting to lay out up here. This actually will need to have these addresses passed through to it if the DMA or busmaster devices need to write to that memory. So these are just some of the complications for this design. Then if we look at the other bus here, so this is the system address bus. This goes out to the ISA bus to other cards and is generally what all of the other peripherals are going to be looking at. And then in the PCAT, when we were going through the comparisons for the original PC, the XT, the AT, then in fact this latchable address 23 down to 17 was actually added with the PCAT. And the reason why these are latchable is that the signals here may become available a little bit earlier in the bus cycle, and this just allows devices where the timing could be tight to decode these things rather than having to wait for the latches down here. And you'll notice that there are some control signals here. So the bus hold acknowledge active low, and there's also bus hold acknowledge as well. So there's the two signals here. They both mean the same thing. When bus hold acknowledge is high, it means that the CPU has given up access to the buses. And so in that case, then these will be disabled. And in fact, when the CPU is given up the bus for this one, then it will be active low. And you'll see that the bus hold acknowledge is used by these three chips, and the active low bus hold acknowledge is used by these chips as well. Then we've got our processor address 20 handling. Because the original PC and PCXT only had 20 address lines, that was going A0 up to A19. The way how the 21st address line, or LA20, is handled, there's a setting here that was introduced on the PC-AT that when the low A20 is low, then in fact the LA20 line is set to 0, and when this is high, then in fact the PA20s pass through the processor and actually goes on and makes the full address space available. And this was introduced because there were certain programs that relied on the fact that the 1 megabyte of RAM would just wrap around at the top of 1 megabyte back down to the bottom, and so this is a way to enable that, and this is one of the things introduced in the PC-AT. And you also notice down here, this other buffer has got a number of the control signals, so the write, read control, the data, command control, and the memory I/O. These are going through this latch here, and I've then got the latched versions of those signals. And there's also the PA18 and PA19 to get the system address 18 and 19 for the ISA bus. So some of these address lines are available both in the SA form and also in the latchable address form. So 17 up to 19 can actually be used in either of these two forms. However, because of the way how the address latch enable works on these latches here, then you may actually be able to see the latch value a little bit earlier with the outputs from the LA buffer here. So to start with, I'm going to wire up this chip over here. So a lot of these inputs are just tied to 5 volts. So there's only one input gate used here. And the low A20, we're just going to tie to ground for the moment. This will come from the keyboard controller. There's one of the output ports of the keyboard controller this will come from. And again, at the moment, the hold acknowledge will probably tie that to ground until such time as we start to look at that. Then we'll see that we need to wire up all of the SA lines here. So SA2, for example, needs to be wired up between these two chips, all the way up to SA9, SA10 to SA16. So just going to wire up this one and our SA2 to SA16 lines. Okay, so that's all of the address lines going along the SA2 to 9, SA10 to SA16. The LA20 output here goes to here as well. Now what we are going to have to do, similar to over here, is connect up the PA2 to PA9. It's going to have a jumper cable going over from here to here and from here to here. But again, we'll do that later once we've done all the other wiring. So now we're going to need to wire in the various control signals. So this one here is going to go off to our keyboard controller at some point in time to enable the low address LA20 handling, should we need it. So first of all, we're going to do the bus hold acknowledge active low, and that is connected to this top chip up here and then these two ones here. Then we're going to have the active high bus hold acknowledge, that's on these two chips, and then also one down to the lower one on the right. So you can join these up around this row here. So now we need to do the address lines from up here down to here. See PA18 and PA19. And we just have to do the address latch enable between these two chips and down here. Okay, so that's done all of the address lines there, apart from these connections coming across here. Now there's just a few more signals down the bottom here. So you can see that we've done this one, and this one, but there's a couple need to be tied to ground. Then we've got the memory I/O going to the CPU, data command, and write read, another tying to ground, and then these are going to be outputs, which we don't have anything to connect these to yet. And we've already wired up the address latch enable, so just wire these up. Okay, so that is now all wired up. Now, I'm going to break the video here because to wire up the rest of this is really going to take quite some considerable time. If we zoom back out here, to wire up this section down here is really going to take quite a while. So I'm going to break the video here, and in the next video we'll be looking at setting up all of the CPU control logic and state machine, and this contains a lot of these PLDs that we've been looking at over the last number of videos. In this video, we've been wiring up all the data latches and data buffers over here. We've still got the ribbon cables to go over here, but we'll add those in the last. We've done a lot of the address lines over here and a couple of the control lines down here. Wired in the reset circuit, the clock, and the power supervisor circuit as well. But in the next video, we're going to have to populate all these sections down here, which is going to have an awful lot of wires going everywhere, so it's going to take a little while. So if you don't want to miss out on future videos, then please hit subscribe. And if you found the content interesting, please hit like. It just helps to make the videos available to more people. If you'd like to leave comments below, then I do try and get back to you within about 24 hours where I'm able to. Thanks for watching.